So our next theorem was contraction on a ball. So the theorem statement is let T be a mapping on a, this will be on a complete metric space X. That means this T is from, just a second, T is from X to X, and suppose this T is a contraction on a closed ball, and this Z is defined as the element X will be there, means that the distance between X and X naught will be less than is equals to R. First of all, let us understand this. Okay, so this is a closed ball and this is defined as Z, and this X naught is a center of this closed ball and R is the radius. So all the points including on the boundary or inside this closed ball will be in this Z. Okay, as you have seen, I have pointed Y on the boundary and one element X inside the circle. So all the points in the region inside this closed ball and on this boundary will be in this Z. Okay, okay, so this X naught is a center and this R is radius, and the inequality is of less than is equals to, that is T satisfies this condition, that distance between the images of the element where X and Y belongs to that closed ball, and the distance between the images is less than is equals to alpha, this is alpha, and the distance between the elements. Moreover, assume that this the distance between X naught and Tx naught, this X naught is the center, this will be less than 1 minus alpha R. It is somewhat like this. This is just to give you the idea. This is your space X and this is your codomain. Contraction is from here to here, and this Z is inside this. Okay, let us say this Z is inside this, and we took two elements X and Y from here. The image of this X will be T of X and T of Y. So it is talking about the distance between the images, and the distance between these two elements will be dx y. I hope now it's clear. This circle, this closed ball is this. Okay, and then the iterative sequence xn, this is like this: T times contraction on this X naught, like x1 is equals to T1 X naught, x2 is equals to T2 X naught. This is the iterative sequence, and this is converging to an element X that belongs to this Z, that closed ball. This X is a fixed point of that contraction T and is the only fixed point of T in Z. This X will be the only fixed point in that closed ball. Let us recall it once again, that a contraction on ball in a simple words is, we have took the contraction mapping from this X to X, we have defined closed ball like this, and this contraction satisfies this condition, and we have assumed this. Now then this condition will hold, that the iterative sequence xn is equals to Tn of X naught will converge to the point X, and this X belongs to the closed ball, and this X will be the only fixed point of the contraction mapping. Now continuity, a lemma is there, a contraction T on a metric space X, that is contraction mapping is on the metric space X, it will be a continuous mapping. This mapping T will be a continuous mapping. Next is fixed point theorem. So we have two fixed point theorem. Even you can say that we have a Schauder's fixed point theorem also, and we will discuss it because it is a generalized version of Brouwer, so we will see that also. So in the Brouwer's fixed point theorem, statement says that we have a T mapping, self mapping from PQ to PQ, and it is a continuous function. Okay, then it says that if we have a continuous function, then that continuous function will have a fixed point. So given this, T is a continuous function, and required to prove is that this T, that contraction mapping, has a fixed point. So we will discuss this theorem in two cases. First case will be very simple. Let us say that this is a domain, okay? You can take it as this is a domain and this is codomain, and from here to here our mapping is T. Let us say in the first case that simply this P has an image. If we transform it, it will have a same image P, okay? So T of P is P and T of Q is Q. So simply, if this is the case, then the result is true, because if T of P is equals to P, then P is a fixed point, or T of Q is equals to Q, then it is also a fixed point, and this is what we have to prove, that T has a fixed point. Then the result is true and there is nothing to prove. In the second case, we have to that T of P is not equals to P and the T of Q is not equals to Q. So we will get C that belongs to this particular interval, and if this P is not equals to T of P, so somewhere it will be equals to somewhere else, okay? And we have named it as T of P. Similarly in Q, if it is not equals to T of Q, so I meant to say that it is not equals to T of Q, or you can say that image is something different. We are getting the image of P over here, not over here, okay? Both of these points are not equal. T of Q and Q, both of these points are not equal. So we are getting the image of P and Q somewhere else, not at the same point. So from the diagram itself, let me make it more clear. From the diagram itself, you can see that this T of P, this T of P is greater than P, you can see, and this T of Q is less than Q. From the diagram, it is very clear that P is less than T of P and the T of Q is less than Q. If I shift this P on the right hand side, so it will be T of P minus P, and that will be greater than 0. Basically we are shifting both of these term into one side, okay? And we will get T of Q minus Q is less than 0. Based on this, we have considered a function like replace P and Q by a journal. We have replaced it with X. So the function is defined as S of X is equals to T of X minus X for all X belongs to this interval P to Q. We have named it as equation number A, or you can say it equation number 1. And since P, if I equate X is equals to P, so this will be S of P is equals to T of P minus P, and this is greater than 0 from over here. And if we will replace X is equals to Q, so this will be S of Q is equals to T of Q minus Q, and this is less than 0. So from above two equations, we can clearly see that S of P is greater than 0 and S of Q is less than 0. So this implies that S of P is this and 0 is greater than S of Q. And as S is continuous on this interval, why this function, the function which we defined, is continuous? Because you can see that this function is made from T of X minus X, means it is the difference of two continuous function. T is continuous, we already know, and we are taking the point X from the interval only. So the difference of two continuous function is also continuous, and hence we can say that S is also continuous. So by intermediate value theorem, we can say that there exists C that belongs to the interval P and Q such that S of C is equals to 0. What this intermediate value says, that if we are taking a point that belongs to the interval, at that particular point our function will give the value 0. And if it is giving the value 0, that means just replace in equation number A, replace X is equals to C. So this will be T of C minus C is equals to 0 from equation number A, and shift this minus C onto the right hand side, so we will get T of C is equals to C, and this is what we want. We want the fixed point, and here C is our fixed point, and hence our result. This completes the proof. So we have some generalized version, and it is basically based on the dimension. The theorem is same, but if we talk about this in a plane, Okay, so plane, that means if you're talking about in 2D, two-dimensional, so every continuous function from a closed disk to itself has at least one fixed point. This is what our theorem says, that every continuous function t has a fixed point. So while talking about plane, that is 2D, we say every continuous function from a closed disk to itself has at least one fixed point. Second is Euclidean space. So every continuous function from a closed ball of a Euclidean space to itself has fixed point. It is as same as we have just said in the plane. A slightly more general version, now we are talking about convex compact set. So every continuous function from convex compact subset K of a Euclidean space to K itself has a fixed point. You can see the theorem are almost same. They are saying the same thing, but we're talking about different dimensions. And now comes the Schauder's fixed point theorem. This is more general form. So what this theorem says, every continuous function from a convex compact subset K of a Banach space to K itself has a fixed point. The only difference you can see in both of these theorems, in the Brouwer's fixed point theorem, we talk about finite dimensional, and in the Schauder's fixed point, we talk about infinite dimensional. So this is the major difference in both of these theorems. Otherwise, the statement is just a generalization of the Brouwer's. Next, we have a Banach fixed point theorem, and we will discuss this theorem in our next lecture, as well as I will tell you more about this convex compact subset or set. We will just discuss it little bit more deeply. And if you have any topic up to this, you can tell me in the comment section. I will cover it in the next video. And as I've already said that these lectures are available in Hindi also. You will get all the lectures in the playlist. I'm just remaking these videos. So yeah, that's it. Okay, thank you. Bye bye.